Hey, welcome, buddy, to the Great Debate Community Channel for another math hangout. Yeah, we're going to be discussing math again a little bit today because
some people the horrors.
The horror of math. No. Some people have actually been requesting this. So this particular one is going to be on linear equations and how to solve linear equations and systems of linear equations. Now, linear equations are not terribly difficult. They are tedious. So this might bore you as we go along, but if it does, just hang tight. It'll make sense if you haven't been exposed to it before. One of the reasons I'm doing this is because eventually we want to get into matrix theory, and as I suggested to EO here, there's really no point that I can see to explain matrix if you don't understand linear equations. So I wanted to do a quick and dirty introduction to linear equations and system sets of linear equations and how to solve them and different methods to solve them. There's no one specific way to solve these. You could do them multiple different ways. I'm going to show you two ways. There's, again, many more than that, but I'm going to go two, which is what's called substitution and elimination methods, and kind of show you what we're talking about when we're coming to say a linear equation. So most of you probably have this before, and most of you kind of will remember back to high school days, because this is, well, not going to be junior high kind of stuff, but it's still something that people haven't used in quite some time. Now, Midnight, when I say linear equation, what do you think those kinds of equations deal with? If I say linear,
lines,
correct? So let me screen share here, and I actually got the presentation and a little handy dandy graphing program that I love called Desmos. It's awesome.
Oh yes, I've used that before. It can't seem to do limits still.
I haven't tried. Well, I haven't tried that. I don't think it'll graph that, but I'll practice at that.
No, I was trying to find limits. You know, if you go down at the bottom, there's like this little keyboard thing. You know what I mean? At the very bottom, where you can go find various functions.
I haven't tried yet.
Anyways, go ahead.
Let me try to get through this, Midnight, because it's going to be a long presentation here. If not, so yeah, we're right. So linear deals with a line. So a line would be anywhere I have a y that's equal to something like here, like 0. Okay, this is a line that goes right down the x-axis, right? There's no change in y. Y doesn't go. There's no line that's going up. There's nothing down. It's just a simple constant, right? Here I have the constant 0. If I decide to make y greater, that y is going to go up because of my intercept is going to go up. So if I say y equals 2, okay, my y-intercept, if you remember, that means where the line intersects with the y-axis. And hopefully you guys remember system. This is your x. This is your y. This is your independent. This is your dependent. And if I go negative values, what do you think that line is going to go? Which direction?
Down.
Down. So it's going to move down. So if I say y equals -2, it's going to intercept on the y-axis at -2. Now, equations for linear equations generally have a specific form. There's actually different ways of writing this. You may have seen it expressed as ax plus bx plus c equals 0. That's a general form. I'm not going to get into that, but most likely you've seen this way of expressing it before: y equals mx plus b. And what this is really just saying is that the b is the y-intercept, which means where the line is intersecting on the y-axis, and m is going to be the slope or the gradient, which I'll explain here in a second. So in this form, the very first equation I have here, okay, is y equals x plus 0. Now, if you remember, we talked about it yesterday. What's the coefficient of a variable if it's not shown? What's its implied coefficient? Anybody remember?
Implied coefficient is always going to be 1.
It's going to be 1. So I actually have 1x plus 0, which is in this form, right? 1, m equals 1, x equals x, and plus 0. So in this linear equation, y-intercept is at the point of origin. This is called the origin, or 0, 0. And if I start changing that, if I change the value of x, what do you think is going to happen?
Wait, hold on.
What's the difference there?
If you change x, it's also going to affect y, isn't it?
Yeah, the slope is going to change dramatically, right? Because for every 1 y, I'm getting 2x out of it. So if you look at the first equation, right, if I say x equals 5, I'm going to go over 5. This is called your run, okay, on the x-axis. This is called your rise, or some people call it fall, but I like rise, but you can call it fall. So if I go over 5, y is going to equal to 5, right? Because it's 5 plus 0. So I go up 5. So I'm going to intercept at 5. So for every value that I stick in for x, that's where my y is going to be. So if I say x equals 10, I go over to run 10, I go up 10, boom. And if you remember these systems, these Cartesian coordinate systems, you used to do plotting, right? You used to be able to plot this stuff. This is why you plot it. You get a couple different points, right? If I take 2 points of any system on this graph, I can plot a line, right? If I have 10, 10, and I have 0, 0, I can draw a line through them, and then I have the slope from there, and I can get a lot of information just off 2 points.
Yeah.
Okay, or 2 pair of points. So, or 2 pair. Now, as I increase the slope, right, that line's going to get more and more steep, as you can see, because here I have, for every 1x, I have 3 times it. So my run will be 5. If my run is 5, what do you think my rise is, Midnight?
Wait, what was that again? Okay,
if my run is 5 here in this equation, 3x plus 0, what do you think my rise is going to be?
15.
15, way up here, right? So as you can tell, it's getting closer and closer to vertical. Boom, boom, boom. So it gets more and more steep.
Yeah.
Now, if I start,
but sorry, I just want to. I mean, I know that this has nothing to do with this, but also, also lines are always, excuse me, are useful when it comes to finding the derivative, tangent line and secant lines. I just thought I'd throw that out there. I know it has nothing to do with linear equations, but
it does relate to what we talked about the other day. The derivative, right? If I have a line like this, the derivative is equal to the time rate of change of a function. So if I have a function, I wasn't going to get too much into this, but if I just put any function, this is what I put.
Yeah, I don't mean to derail. I'm just, just like.
That's okay. I mean, it all depends, boils together. But if I put a function just like this with a parabola, the time rate of change at this point, this is a tangent line at that point, which is actually going to be not that.
Well, technically, wouldn't there be the secant line, because it's going to.
Secant line is going to intercept at 2 points. This is at 1 point. This is actually my tangent line of this function, right?
I know, but the line you were showing before, at least to me, seemed like it was going to 2 points if you zoomed in. No, the other one.
That one, yes.
Well, that one is. Yeah. But there were also the other one you had. If you zoom in, it is going through 2 points.
Yeah, the way that works is, as a secant line, you have 2 points, and as that converges to a point on the function, that is how you take. That is what you're doing when you take a derivative. That's one of the first principles of how to do a derivative, is to do it that way. That's graphically, right? Yeah, do you want to add to that, or?
I was just going to add a good way to remember: secant means to cut, and tangent means to touch. So secant will be in 2 points. We'll cut the graph and intersect it twice, and the secant line, the tangent line just touches, so it intersects it once, as Steve mentioned before.
There you go.
Yeah.
Okay, so if I start playing around with, we already know if I change the coefficient to the x, but if I start changing around the y-intercept, or the b, look what happens. If I say y equals x plus 1, notice the shift from the original equation. Okay, I've actually gone from the origin to the y-intercept 1. Because this right here, b, is equal to my y-intercept, right? So all I've done is I've done a shift. I've shifted this line, which is the slope hasn't changed at all. I've just moved it up 1. Okay, you see that, how that works? And if I move it down 1, it'll go down there, right?
Yeah.
Now, let me ask you.
Point out that these lines are parallel.
These are going to be parallel lines. Let me ask you. Do you remember? This is kind of off topic, but it's good to know. The b gives you the y-intercept. Do you remember how to get the x-intercept?
You put y to 0.
Close. Close.
Oh, go ahead then.
You put x to 0. Look what happens when I put x to 0. I get y equal.
No, he was right, Steve.
You're right. Yeah, you're right. I'm sorry. I'm sorry. You're right. You get y to 0. Yeah, you're right. So if I get y to 0. Now I subtract 1 from either side. I'm left with x equals -1.
Yeah.
Which is right here. Yeah, you're right. My bad. I'm sorry. I knew that.
I wasn't sure.
No, you're right. It's y to 0. See how long it's been since I've done this? But yeah, you set y to 0, and that's going to give you your x-axis intercept, because literally you're just putting 0 equals x plus 1. Move the 1 over the other side. You're left with minus 1 equals x. So that's how you find the x-intercept if you need to.
Hey, Steve, would graphing a line segment count as a linear equation?
A line segment is still it still has the same properties of a line. You're just taking a segment of a line. The only difference between a line segment and a line is infinite in both directions. A line segment terminates, right? You have line, ray, and a line segment, right? So a ray starts an origin and then goes on for infinity. A line goes infinity both directions, and a line segment.
Yeah.
The principles are the same, right? You're just taking a segment of that line. You're taking a section of it.
Yeah.
But the slope of a line segment on the parent line is going to be exactly the same. No matter where you take the slope of that line, it's going to be the same.
Yeah, the graph of an absolute value function could be considered 2 rays.
Yeah, because you're gonna have a point of origin, and then you have like a V formation, and those are going to go off. Yeah.
If I may, Steve, any 2 points uniquely determine a line, but what's interesting about the equation you used, it's also true that just 1 point, namely the y-intercept and the slope, will also uniquely determine a line.
Right, and we're gonna get into that a little bit too. Also, by the way, I'm drinking coffee. It's so delicious. We should also mention that I forgot what I was going to say. The line. Oh yeah, there's just as many points on a line segment as there are a line, which is confusing to a lot of people. If you have a line segment that's an inch and you have an infinite line, they do have the exact same amount of points, which is an infinite amount of points, even though one's much smaller. That gets to mess with your brain a little bit, but that's actually true.
I think the term they use is infinitesimals.
Not really, because the reals don't have infinitesimals. There's something called I believe it's called the is it the Archimedean principle? The
Archimedean principle states that for every. Okay, here we go.
Well, you're making me pull
every
this.
real number, there exists n so large that 1 over n is smaller than e. Did you follow that?
Yeah, that's
for every real number. There exists n so large that 1 over n is smaller than e.
Yeah, that's the epsilon, by the way. When he
says
it
1 over any letter for any real
number.
Well,
but E there stands for epsilon.
You can. That's the letter we use. That's the letter we use. It doesn't matter.
For Cauchy sequence.
Are you looking at the side of what Dragnot said? Maybe you saw it.
No, why?
Well,
I don't have the chat open. I have the outside chat open, not the internal.
Oh.
There we go. I do now. Oh, I had it. What am I looking at? What's the question, Drag? Go ahead and interrupt if you got a question. Somebody from the outside has got a question.
Well, I was just putting up notes because I'm talking to folks as we're having a conversation.
Okay, so these are why we come back to, or?
Well, I just wanted to mention. Well, folks are wondering why we have these things in the first place. Why is finding slope useful in measuring things? Like what would someone use this for? And its other applications such as finding the derivative.
Yeah, these all lead to other things. For example, like when we talk about derivatives, this is what we're kind of doing. But back to what EO was saying, the principle of infinitesimals basically means that inside the reals there are no infinitesimals. You can't have something that what's the highest number next to 1 that isn't 1? That number doesn't exist. There's no such thing, because you can't have infinitesimals. It starts getting into what's called neighborhoods, which are so confusing that if EO ever has a presentation on it, I'll be happy to listen to, because I still don't understand neighborhoods.
Right. I mean,
they're crazy complicated.
There is no smallest positive number, and there is no next to when you have a continuum. But this is pretty high level set theory, Steve.
That's high level
set theory. Can I answer your question? So, for example, when we're driving, to find the speed that we're going at any given instant, or I don't know, engineers in cities, we use slopes come up all the time to set, to build houses in your field. To anytime things are changing, we have to use derivatives. Anytime things are changing in a non-constant way, we have to use calculus. So it's a fundamental notion of anything in life. Anything that involves change involves slopes, Drag.
There you go.
Thank you, Newton. And the other guy, I forget.
Leibniz.
Yeah, Leibniz. Thank you.
How did we get
Leibniz? Sorry, guys. Leibniz.
I'm about to say, I thought it was Leibniz.
Leibniz. Yeah.
I can't pronounce it.
How did we get 1 dislike already? See, who doesn't like math?
I advertised this
no, it's
this
okay.
on my channel, so I have a
The
feeling.
one dislike, you will fail this in college, by the way, just FYI. You know,
if you ever went to college. But anyway,
if you ever went to college, if you ever got your GED. Okay, so back to our presentation here. So in this equation for the mx plus b, it is in the form like this, right? So I have mx plus b. Here's m equals 1. 0 is the y-intercept, and if you notice, it's the exact same line here, right? They're identical, right? It's just this one you can actually see it because it's in the coefficient, right? And if you really wanted to put it right, it'd be y equals that. Okay, so we kind of understand what's going on with what we're talking about with lines now, because I'm gonna close this out here. So let's get back actually to the about as far as the line itself. Now, you guys may remember the equation here. This is the slope equation. It's written different ways. I've written it actually a couple different ways here. I prefer it this way, which is basically an easy way to remember is your slope,
delta y over delta x.
Is your delta y over delta x. And a delta means what?
Delta means a change.
Means change. So I am taking the change of something. Here would be the x, the second x, the position of x minus the first, right? So it's basically going to be y2 minus y1 over x2 minus x1. And if I look on the graph here, let me get the graph. Okay. One sec. Let me show you on the graph. There we go. So according to this, right, if I say 5 minus 0, 5 minus 0, well, what happens here? Where is my intercept there?
It's 1.
Or what's my slope? It's 1, right? Exactly. Because my slope is 1, which is my coefficient right here and right here, right? So my slope is 1, but that literally means what I'm showing you right here. When I take the difference, the delta of the two positions of y over the two positions of x, I end up with the slope. So here, the complete formula of y equals mx plus b.
Correct me if I'm wrong, but isn't y2 minus y1 equals m times x squared, x2 minus x1 the point slope, or is that the like, you know, here's the name.
Yeah, it's the same thing.
Slope formula. Yes.
Point slope formula. Yeah. Mm-hmm.
Yeah, I know. You know, you
because you're taking it from points,
that,
right?
So, yeah, you just didn't mention that. I figured
there's different ways of writing these things. There's different ways of many different ways of looking at it. Like, for example, like I said, this equation mean the same things. I just find like the compact form because I think it's easier. And if you know what delta means, you can figure out it means, you know, the change of y over change of x, right? To me, it's a lot easier to write out this than this. Now, when you're learning this in like whatever 8th grade or 5th grade, I don't know where the hell it was. You write it out like this because they want you to understand the concept, right? Would you agree?
Yeah.
Okay.
I wish I paid more attention in school. Sorry, go ahead.
No problem. We all do.
So sorry, Steve. This is a really important point. Students, make sure the indices line up. Often you'll see people write y2 minus 1 over x1 minus x2. And if you do that, you'll get the negative of what you intended. You have to make sure that you're consistent with your indices.
Yeah, definitely.
And these are your indices, by the way.
Oh, I would definitely do that. I would do, okay, well, y1 minus y2, and then not realize what I did wrong until later. And it is very important to remember.
We all have.
Oh yeah.
Yeah. If you end up with if not, you're gonna end up with the wrong slope.
Just fucking write the formula over and over. Like, here's what I did when I was taking physics. Physics is nothing but memorizing fucking formulas right after you learn the concepts.
Well, that's why I like this one, delta y over delta x. A lot easier to remember because of dy dx, right?
It is, but so, I think like if you ever plan on taking a physics course, they need to learn the actual form. Like, you can understand the concepts with the deltas, but then you need to learn how to manipulate the formula because the questions that you'll be asked will give you certain variables, and then you have to find the other variables, which a particular formula that you may or may not have memorized may or may not contain. So understanding how to manipulate that formula will be actually a part of solving that problem.
Yep. Okay, so in this formula, we've realized that for the general form, it's actually the line form, but mx plus b, the slope is 1 and the intercept 0. We all agree? We all on board on that? So let's start using an example here, okay? So this is going to be a very, very simple equation. Okay. Can you guys see it down here?
Yes.
Or I got to show it more.
Well,
right.
we'll go down a little bit more since we're doing an example.
Well, you know what? It's okay. We'll just show it out right here.
Yeah.
It's okay. So let's work through it. Okay. This is a linear equation, right? It's in the form. It's in the proper form because you have the coefficient x plus b, right? So this is the same form as this. A lot of times, again, we're relating to a form, and this way of writing is in this form already. So the first thing you would want to do is you want to isolate your x on one side, and the best way to do that is what do I want to subtract from both sides of this to get x isolated? Minus 4. So now I have
from both sides.
Now I'm left with 5x equals 15 because I've subtracted 4. These go away. These cancel out. And by the way, I might put a pen and thing, whatever, tablet on my wish list, and see if I can actually integrate this where I can actually do this kind of math by crossing it out to show you guys. So maybe a benefactor might hook me up with that, because I think it might help if I'm able to show you how these things cancel out, and especially in future presentations.
Yeah, Steve, when you made this presentation, you should have made x equals question mark. So so you could have asked. I mean, it's obvious what 15 divided by 5 is, but
yeah, and I'm not worried about doing it that way. You guys can see the steps. I mean,
oh yeah,
if this was a brand new thing, maybe, but I mean, I'm assuming most people have had this. This is kind of more of a refresher because, like I said, when we get into the matrix, you're going to have to understand these concepts. So,
I want to. Matrices are kind of confusing. You gotta switch rows and
right.
Anyways, go ahead.
All right. So I'm now left with 5x equals 15. Now, what do I divide by each side to isolate x?
5.
Okay. So those 5 over 5 cancels out. 15 divided by 5 is 3. So I'm left with x equals 3. Now, you should always validate and verify your answer, which I didn't do here for save of space, but I think I did on the next one. But if I validate this, how do I validate that this is the correct answer?
You plug 3 into x, and
so 3 goes into x. 5 times
so
3
it's
15 plus 4. I'm left with
19.
Okay, so that's how you'd validate that. That's how you know you got the right answer.
So if I may, Steve, just a general comment. You had a linear equation in one unknown, so all you needed was one equation. If you go to 2 unknowns, namely x and y, you need 2 equations. Otherwise, it'll be what's called underdetermined. And finally, a final comment. The whole reason this works, does anyone know what algebra means? I'll give you a hint.
I know it's Arabic.
Arabic. Yeah, Kareem Abdul-Jabbar. You guys heard of him?
Yeah.
So there was a manuscript, and I want to say, please check me, in the 11th or 12th century. Anyway, this Islamic scholar, basically the title means balancing, and that's really the foundation of algebra. What you do to one side, you have to do the other. So everything we're going to do here, so notice what Steve did. He subtracted 4 from both sides, then he divided both sides by 5, and that's going to be the principle of everything we're going to do going forward. What we do to one side, we have to do to the other, balancing.
Think of this as a teeter-totter.
I did not know that. Yeah, I did not know that.
If whatever I put on one side of the teeter-totter or scale, I've got to do the other side. Whatever we want to look at it, like a seesaw or like a scale. If I do something to the left-hand side, I've also got to do the same thing to the right-hand side.
I don't know. I think about it. It makes sense.
So let's move on to what happens if we have 2. This was a single variable, right? Not that difficult. So let's look at what happens if we have 2. Okay, this is called a set or system of linear equations. Okay, so when they say, you have a set of linear equations, this is what they mean. I have one linear equation that's based upon this. I have one linear equation upon this, and then they're bracketed, meaning that they're set together.
Yeah.
The first method I'm going to show you, guys, is called the substitution method, which is generally easier, especially for 2 lines. For 3,
yeah, for 3 lines, I guess a little more. I've done the 3 ones. You got to do a plus b, then a plus c. Yeah, you're right. It gets confused. Go ahead. Sorry.
Okay. Yeah, hang type there, Brent. Hang type. Okay. So here, what I'm going to do is I'm basically going to try to find one variable and substitute it into the other equation. So you could pick either one. I pick this one, right? Y plus 2.
It's easier.
So how would I go about isolating y on this? What did I do to get to here?
You minus 2y on both sides, thus making x equals 11 minus 2y.
That's all I did. all I did was subtract 2y from this side, which means I have to subtract 2y from this side. Now I have another linear equation, right? I have a new form of it. Now I could take this and substitute it into this x here, right?
Yeah.
Okay, so I'm just taking this. I'm just taking this and I'm substituting it here. Now this is going to give me 2 times a parenthetical group, right? This is what your x was, plus 3y equals 20. Then what method do we use to figure this out? What's that called? Starts with a D.
The distributive property, and I think you're missing a y. Because I mean, it's 2 times 11 minus 2y. So it's 22 minus 4.
Oh, the second line.
Hang on.
And the second line, you're missing a y where the 4 is.
Oh, no, 4y. You're right. You're right. Good catch. Okay, let's fix that real quick. There you go. Yeah, that's a good catch. Okay, so
what would you do without me, Steve? I'm kidding. Go ahead.
Yeah, there you go. Correct. Yeah, that's it. We check each other. But you know what? At least you knew what was going on enough to point that out, right?
Yeah.
So this is actually called distribution of multiplication over subtraction. Have you heard that before?
Yes, multiplication. Yeah, go ahead.
Because what I'm doing is I'm multiplying over a negative symbol, right? Which is a unitary operator.
Yeah.
Actually, this term. So there's different forms of distribution. This kind of distribution is a multiplication over subtraction. So I'm going to distribute this. I get 22 because 2 times 11, 22. Then 2 times 2y is minus 4y. This stays the same. This stays the same. Okay?
Yeah, so then you have negative y equals negative 2, y equals 2. I'm sorry to stealing your thunder, but...
Hang on. Slow your roll. So, because I want people to understand. Now, I'm going to combine these two terms, right? Which is negative 4y. Now, here's something that's very, very, very critical. This is where people get a lot confused in mathematics. This symbol is attached to this term. They are one. Okay? This is called a unitary operator. This is negative 4y plus 3y. So I have negative 4y plus 3y, which is going to give you negative y. Because I have negative 4 of something, and I'm just adding 3. I still have a negative. I still have a deficit, right? From 0. Right? So 22 minus y equals 20, right? This hasn't changed. I then subtract 22 from both sides. This goes away. I'm left with negative 2. And then how do I get to here? Because I don't like having negative y's and negative x's, and you shouldn't, obviously. So what's the best way to get?
You divide by negative 1.
Or I just times by negative 1.
What?
Well, negative 1 times negative y is 1. A negative times a negative is a positive, right?
I said divide.
But you times.
I suppose you could times too.
Yeah. So I'm left with y equals 2, right?
Yep.
Okay, so now we've actually found a variable. We found actually what one of them has to be. So we know y here is actually 2. Now we go back. Yeah, I mean, you could do it either way. You could divide 2. I'm not saying he's wrong. I'm just saying that you should probably multiply for various reasons going forward. But either way, you're going to get the same answer, right?
Yeah.
I try to avoid divisions. Division, if you think about it, it actually in higher maths, division doesn't really, and Neil's going to kill me on this, but division doesn't really exist. Okay? It's only multiplication and addition, because division is the reciprocal function of multiplication. So you really only have multiplication defined in higher maths, in what's called abstract algebra, and you only have addition, because subtraction is just the inverse function or the reciprocal function of addition. So technically speaking, you do have it defined. Division is defined. It's defined as P over Q, where Q is not equal to 0, right?
So technically, there's only 2 operations then, plus and adding and subtracting, and the other 2 are just reciprocals, or
of the other ones, right? Yeah.
Interesting.
So like I said, division is defined, but the problem is division is, like I pointed out the other day, is a partial binary operator, because you don't have division by 0 in the reals, right? All right. So moving on. So let's substitute it. So when I put 2 back in this equation here, right, what do I get? I get 2x plus 3 times 2. Remember, this is multiplication. Nestling will like the link there, Drag. So I left the 2.
Mac was off.
Yeah, Nestling.
Oh, let me get him in.
So 2x plus 6 equals 20. I subtract 6 on both sides. 2x equals 14. Then I divide each side by 2. I'm left with x equals 7. This is my answer. This is the solution to this system of linear equations. This is my ordered pair. Okay, so x equals 7, y equals 2.
Okay, verify.
Now we verify it, right? So when I verified, I'm sticking in what I believe was the correct answers, right? And I put in, for here, I put y equals 2, and 7 plus 4 is 11. 11 is equal to 11. Good. I put 7 into here, and 2 into here. I get 14 plus 6 equals 20, and 20 equals 20. There you go. So we know that these are the correct answers, right?
Yep.
Everybody on board? Everybody good? EO, we're happy?
So is this hangout about searching the value of the circumference of pi?
No.
I mean, I think we need to stress the verify your answers very, very much, because that's something that people overlook, and they think, well, I did it quick and I did it smooth and it's right, and that's not necessarily true. And it'll come into play, especially with quadratics, when people will, for a word problem, give you a negative answer for a height. Which, how do you have a negative height?
Well, you can if you have baseline 0, like from the Earth, but I think
well, yeah, if you're going below the Earth, but if you're trying to determine like the height at which a ball reaches terminal velocity, it's not going to be negative.
Right. There's certain instances where in a quadratic equation, because of physical reasoning, you can't have a negative. For example, like negative pressure, or not negative pressure. I'm sure you can have negative pressure. Negative. Well, let me try to think here. Negative. You can have what could be. What's something like, oh, negative volume, right? How do you have negative volume, right? So there are certain limitations where even though there's answers to the quadratic, it doesn't actually work because of reality. And so that second answer that you get is not an actual answer. You don't give it.
Yeah, it's usually ignored. If you solve a quadratic and you have 2 numbers and one of them is negative, you usually pick the one that's positive. Because, as you said, you can't really have a negative area or a negative, or could you have?
No, you can't have negative area.
No, not a negative area. Yeah. No.
Yeah, but you got to be real careful, because there are times you end up with weird imaginary stuff that still are correct answer, right? You know, because careful of the music. So,
I got you, Bullion. Hold on.
Remember, the imaginary number isn't in reality, but it is part of the solution set, because technically the I is actually your rotation around the x-axis, if you want to look at it that way, right? So that, because you have a Cartesian system, the x and y, you can't really show.
Sorry for that, Steve.
What you're actually showing with the I is what's called the rotation around. And you're actually, when you start learning about sine and cosine and pi and all that other kind of stuff, you actually see how the imaginary component factors in, because you will go over this eventually, called Euler's formula, which is e to the I theta equals cosine theta I sine theta. Very, very prominent formula. It's great. And that really kind of shows you the different components of the real to imaginary parts of a complex number.
Right, but Steve, you might remember, you'll only get complex roots in conjugate pairs. In other words, you'll either get 2 real roots or a repeated root, or you'll get a complex pair. But if I may, Steve, for younger students, a good way to check the solution too is to graph both lines and see that the ordered pair you got as a solution matches up. However, the problem is when we get into system equations 3 by 3 and higher, we lose all sense of intuition and we can't draw them anyway.
Yeah, and by the way, there is another way to solve these called the graphing method. I'm not showing you that today. You may have learned it that way as well. Perfectly fine way of doing it. But as he said, when you start dealing with higher, three variables and stuff, it gets really confusing.
Well, I mean, if you're dealing with 3 dimensions, it's a little complicated at first, but once you get the hang of it, you can easily graph them in 3D, 4D, and 5D.
But it's still difficult. A lot of times when you're graphing multiple lines, you're doing them for what's called constraint problems. I'm sure EO could probably do a really good hang on that. But Constraint problems are really cool because they're used all the time, like in business. What is my maximum amount of profit for this by using constraints? By having multiple formulas, it's giving me an area, and that area is the maximum amount of profit I can get based upon how many I've sold, how many units I've sold, the cost per unit. It's pretty interesting, but it's not easy. Constraint problems in calculus are not easy. They're not. I hate doing them.
I think some of the ones with the fence, like you can only have this so much of an area fenced off, and you need to find out how many.
Same principle.
Oh, God,
well, if I got a piece of paper, how many squares can I make out of it by this?
Oh, fuck those problems.
Yeah.
No.
I don't like doing them. They're my least favorite thing to do. I will probably never show you how to do one because I hate them.
Come on, Steve. Do it for knowledge, for learning. You can do it. We have faith in you. Anyway.
I don't like doing them. I really don't.
So I think what Steve was referencing earlier is something called linear optimization, where you have
optimization system.
The maximum of vertices. But hold on, that's not quite related to normal optimization with calculus, finding derivatives. Right. But
that's true. They're different.
We need Ned because that's part of a field called operations research, basic operations research. I want to say with linear optimization and the constraints. You can do it though with this math, but the point I want to make is if we go to a 3x3 equation, so now you guys can see clearly we're dealing with when two lines intersect. When we go to 3x3, we're talking about three planes intersecting, and then whoever said you can do it easily.
Three variables, right?
No, it's three planes, but he's talking about it's 3 planes. Instead of having 3 lines, the line is a 2-dimensional plane instead. So you're dealing with with how 3 planes intersect in those systems.
Yeah, but you also have X, Y, and Z. It's three
right,
variables.
Yeah.
Okay. Can we just all agree? We'll all agree intuition leaves us, and it's really hard to.
Yeah, I don't like doing the system.
Well, I was using hard for a synonym for impossible, just to be clear.
Yeah, I can't visualize that kind of stuff, and I don't even want to bother. So, anyways, moving on. So, let's see here. So we're going to move into the substitution method to solving
elimination. You mean?
No, elimination. Yeah, sorry, elimination. We just did substitution. So elimination is basically the way of adding or subtracting or changing these into a new system in order to simplify them to get a new equation out of it. Okay, so basically what we're going to do on this particular one, right, is if you notice here, if I times this top one, we'll call this the first, and we call this the second. And by the way, it's a really good habit, I think, to label them first, second, and third. Okay, row 1, row 2, row 3, however you want to do it, because matrix, that's what you're doing. You're actually working with row 1, row 2, or first, second, third, whatever you want to call it. So if I times 2 to this whole equation, okay, here I actually get 2 times.
You might want to times by -2. So I know you're probably.
No, let me show you why. I'm already doing a substitution. I'm just telling you I'm subtracting. I want to make it easier, so I'm subtracting. I'm going to subtract 1 from the other, 2 from 1. Okay, so I'm just doing a simple distribution, multiplication over addition. I end up with 2x, right, times 4y equals 22. And I'm just subtracting these, right? I'm just putting a minus here, and I'm subtracting this whole quantity. Okay. And by the way, I can tell you right now, I don't like working with negative numbers. I think I mentioned this before when I was in nuke school. Negative numbers would be my downfall, because when you have big long equations, half the time I ended up with the wrong sign because I've lost a negative sign somewhere along the line. So I try to avoid them as much as possible. That's just me.
Okay, you're doing it your way. I just figured people watching. Go ahead.
Okay, so I'm subtracting this whole equation from the top. So 2x minus 2x is 0, right? Or 0x. 4y minus 3 is, or 4y minus 3y is 1y. And then 22 minus 20 is 2. So I'm left with y equals 2. I've now found the value for y. Now I can go back and substitute y into another equation. Okay? So I'm going to put it back into the top one here, the first one. So I have y plus 2x equals 11, right? And then that's obviously 4. And so I'm just going to move the 4 to the other side of the equation. Y equals 11 minus 4. That should be x equals 11 minus 4, x equals 7. So look at my solution. X equals 7, y equals 2. Is that what we got up here? Yes, it is. So this method, I think, is a lot easier, obviously. I think it was faster than doing this method. But it depends, again, you know, on what you prefer. But sometimes when you're doing these, like in the next step, there's really no other way to do it besides elimination. It's you have to be able to manipulate these formulas to get new sets of new linear equation systems.
So Steve, when we do matrix, when we do matrix arithmetic, it'll all be elimination. So you're right, substitution is inefficient. However, when you're dealing with linear quadratic equations, substitution is often the only way to go. So different tools for different contexts. But yes,
well,
you're right.
We will be doing, even though you're doing elimination method, there is still some substitution.
At the very end, back substitution.
Right.
Yes.
Right. Back substitution. So these all things join together. Now, this is where, again, you start doing real math, okay? Because this is a 3-set linear equation system dealing with, 3 variables, right? You have X and Y and Z. Okay, we need to come up with a system that works to find each one of these variables, okay? And I can tell you right now, if I was to do this using matrix, it would be a hell of a lot easier. Matter of fact, there's a matrix formula out, or calculator, many of them you can find. All you do I'm probably jumping ahead here, but to give you an idea, all you do to solve this in matrix is all you need to know is these coefficients and these numbers here. You stick them in a little grid, you go boop, 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 and then it tells you what the answers are. Okay.
If I may, Steve, what's really cool about most of what we do in math and in Drag's field, any other field, you take a hard problem and make it simpler. So we have a 3x3 system here, everyone. What Steve is going to ultimately do is reduce it to 2x2 systems, which we've just shown we know how to solve. And then we'll solve those 2x2 systems and solve for a single variable, then back substitute, and then back substitute again. But that's basically...
It's a lot of writing, but it's simple.
But hold on. Most of knowledge, and this is really important, you take something that's difficult and you transform it into something that you know how to solve.
Yeah, that's exactly what we're doing. That's it. Okay, so let's walk through it. So I've set up my system of equations here. And remember I told you you've got to do some kind of row manipulation in order to try to subtract or add and get a simpler equation, something we can work with. So the way I did this one, this was actually, I've gotten it from Paul's online notes because the one I created, I didn't want to work out. So I was like, you know what, this one's already out there. So if you want to actually look at this one, it's on Paul's online notes, which everybody who knows calc knows that site. And I'll put the probably link in the description. So
for the win.
Yep. So I'm going to take remember, this is the first, the second, and third, right? I'm going to take this first row here, and I'm going to times it by 2. Okay. So I times this whole quantity by 2, right? I got to put 2 here too. So 1 sec. So 2 works. Okay. So I'm left. I now have a new equation. I have 4x plus 2x plus 2z equals 8. This is a new equation, basically, right? Would you agree? I'm trying to get different types of equations where I can work with them. So I'm going to take this equation, this new one, and I'm going to substitute in for row 2. Okay. I don't need this one right here. I can take this one. I can put it right in here. Okay. And now this is my new set of linear equations. Okay. Now all I need to do is take the first and second, and I can add them together. Now remember, you can add, you can subtract, you can multiply, as long as you're doing the same thing to this side of the equation, to this side of the equation. Oh, not seeing it? Can you see this in the outside chat? Moderator said he can't see it. Is it still presenting?
Let me see. Yeah, my outside chat's out.
Okay.
Bullion, I added you, by the way.
Oh, he's talking about adding you. Okay. So I'm going to add these together, and I get x plus 4x equals 5x. Negative 2y plus 2y equals 0. So the y's go away. 3z plus 2z is 5z. And then I add these together, I get 15. Now I have another linear equation I can use. Okay. Right. I'm going to take that linear equation eventually, and we're using it to put in the system. But before I do that, I can also take the first here. I can take the third here, and I can manipulate that as well. I can add these together, right? And when I add these together, I get Y's cancel out, and I'm left with Z. So I left with minus 2x plus Z equals -3. So now I have another equation I can work with. And you'll see how these actually become important here in a second.
Steve, real quick, I need a spanner.
Oh. Got it.
Somebody's spanning the chat.
No, I need a spanner. I need mods.
Oh. Okay.
Spanner wrench.
You got it.
Right.
Thank you.
Okay. So now I like showing the system that I have, right? The system of linear equations, because this system now that I have, I've now used, I'm keeping the first row, which is this one, but I'm now substituting this one that I came up with and this one I came with to get a new system.
Okay.
So now my new system,
add, notation to this so people can see. I mean, I understand. Well, all of us in here are following what's going on, but is there a way for you to add notation, because now we're at like line 4, 5, and 6, technically, right?
well, yeah, but we're just putting them back into the original system. Anytime you see three things like this, just think of this as the system that I'm working with.
Right.
Right. If you're actually doing this on a blackboard, what you're going to do is what I used to do. It was just I would change this system. I'd erase the line. I'd put the new one in there. Okay. So all I'm doing is this is the same system as this, right? My original one right here in example 3. But now I've got new equations I can work with. I've manipulated the second one and the third one to get a new system set, which is this right here.
Right. We've redone it. So that's what I'm saying.
Right.
Is there, like, can we add a notation there so people can follow this for next time? Like I'll tell you later. Yeah, go ahead.
Okay. So what we're trying to do literally is eliminate variables.
Where did he go?
Was Steve just sniped?
He might have been.
Oh well.
Let's see here. Is that? Wait, no, actually here. I'm sorry. So the second and third, these two equations here. Is that right? Second and third.
Are you screen sharing?
No, I'm not. What happened?
I don't know. Everything went quiet and I had to refresh.
No, I was screen sharing.
You seem to have gone. You seem to have left and then came back.
Me? I didn't?
Yeah, no, you left and then came back.
I refreshed.
Oh, here. Okay, let me see here.
Actually, it's funny,
it's that
Steve,
bug again. Let me
the
refresh.
difficulty that you're
quick.
having, just everyone who's listening, the difficulty in writing out 3x3 perfectly expresses why they invented matrix notation in the first place. You can see
Right. It's just, exactly. It can get confusing really fast. But let me refresh real quick because I have that bug that I had yesterday where it's not presenting. So one sec.
Yeah. Yeah, so that's kind of the issue. Like for next time, and I forgot that this happens when I'm writing this out, I'll forget what line that I'm using, because if I have I forgot what I call them, but if I have new equations, my new set where I've eliminated and simplified, I would give them their own annotation. And so right above them, like in a superscript, I would write, number 4, number 5, and that would correspond with, the original ones, 1, 2, and 3 that we had from the original problem.
I've seen used letters like A, B, and C. That then you add A and B. Then after that you add.
Yeah. People do that as well. You're right.
No, Dred's
That's
right. You label the lines in parentheses. So this is equation 1, equation 2, equation 3.
Yeah.
Refer to them.
There's multiple ways of doing it. It's at the end of the day, it's just a way to. Go ahead. Sorry.
Because that way you can refer back to whatever equation you're working with, right? EQ1, EQ.1, EQ.2. That's a great way of doing it. I didn't do it on this presentation. Maybe for next time I'll annotate a little bit more. Again, this is more of a quick and dirty type thing, but it's a great way to do it that way. So anyways, I'm multiplying this row by -5, and I come up with a new equation, right? Now I could take that equation, substitute it back in here, or for that line, right, that row. I can add these together, and I get. I made a mistake. Where?
Yeah, on the third multiplied by -5. On the right-hand side, it should be positive 15.
-5.
Because -5 times
You're right.
-3 is
There you go.
15.
There you go. This is exactly what I said. Remember, negative numbers will screw your world up. That's exactly, he pointed out. That's what happens. That's why using this method sucks. You don't have to worry about that as much in Matrix, but anyways, it sucks. But that's a good catch. I'm glad people are catching these things because that shows that you're understanding it. We all make little minor mistakes, and it happens all the time. But you're right. So now that I have a new equation, I can add these together, and once I get to this, that's easy right here, right? But I didn't show for some odd reason.
If I may, Steve, yes, it is human to make mistakes, but where mathematicians will, what mathematicians will say is that's why we check our work at the end, because everyone can make mistakes, but you're far more unlikely to make them if you check your work afterwards.
Right.
Right. And the beauty of
so
this
now,
is
but now,
answers and
but now that I've isolated,
plug in.
What now?
And you plug that in, that x equals 2, and you get something that verifies it.
Right, because I'm putting back this is my new system set, right? And I know that 15x equals 30. I can isolate x. I know x equals 2. So now I've got actually a variable, right? And we'll verify this at the end. So if I substitute that back into equation, right? The easiest one to pick is this one because I only have 2 variables, right? I know one of the variables. If I have 2 variables and I know one of them and the rest are constants, I can figure out the other one. So now I can back substitute this in. I get 10 plus 5z equals 15. I then move the 10 over here. 5z equals 5. Z equals 1. Now I've got 2 variables that I know. Now I back substitute again. In this case, I go back to this equation, the top one, because I've already know x. I've already know z. Now I can find y. So I have 2 minus 2y plus 3 equals 7. Add these together, I get 5. I'm just grouping. I like to group on one side before I do anything. And that's good practice to get into is that you group all your coefficients, you group all your y's, you group all your x's. Then I like to start manipulating, okay? Because if you grouped them and you know you're consolidated, you don't lose something somewhere down the line. So here I've grouped the coefficients here, or assuming the constants. I'm now going to move the 5 over here. I'm left with -2y equals 2, so, times each side by -1, and I get, or divide each side by -2, sorry, and I get y equals -1. So now I've got a solution set. I've got x equals 2, y equals -1, z equals 1. Let's check it out. Let's verify it. We'll go back into the original one. So we'll put, you pick any one you want, but let's just pick this one, the middle one, because it's probably easier. So what did we say? We said x was what? Let's go back down here. 2, right? Excuse me. So 4 plus y, which was what? -1. And the z equals 1. So 2 times 2 is 4, plus 1 minus -1 is 4. So we know we've got a right answer. If you validate it here, it should.
Sorry to be pedantic. No, that's not quite true. Do you have to actually check all 3 equations? But it's
that's
fine.
true. Okay, you're right.
But because you can imagine a situation where it satisfies one line, but it
not
doesn't
all of
satisfy.
them.
Right, I'm just being pedantic as usual.
Now you're right. You're right. You can. There is a situations where you can satisfy one, but not all of them. But let's for sake of simplicity, let's assume this is correct. Okay. You okay with that? Because it is. All right. But you're right. If you really want to check your work, you would check each individual linear equation to make sure that it holds true for all of them. So. In a nutshell, the only thing I wanted to finish with is that when you have the equation right here, y equals mx plus b, if you guys remember, f of x is the same as y, right? So the function for a linear equation that you're going to see it written the most is in this form here, which is f of x equals mx plus b. And going forward, that's kind of how we're going to be writing things, and we're going to be using functional notation a lot, which is in this form. So instead of using y here, we use f of x plus mx plus b. That in a nutshell is how you would do simple linear equations, how you do a set of two linear equations instead of three. And then again, we're going to be showing you in a future presentation, maybe not tomorrow, but the next day, we're going to start with basic matrices. We're going to be doing, I'll start with 2x2s, or whatever. There's different, one by one or whatever. It depends how simple you want to get, I guess. But we're going to show you that all you really need to do is use the coefficients, like here 1, 2, and 11, 2, 3, and 20. And by using a matrix, I can actually solve this linear equation system pretty easily. I have to do all this method. So
are you going to show that next time, or are you doing that now?
That'll be my next presentation. Yeah, I mean, I think linear equations, I think people kind of got this down. It's not, we've all had it, so this is kind of just a review.
Yeah.
So I wanted to kind of do it quick and dirty, so at least people understand what a linear equation is, why it's a line. How to do a system of linear equations to solve.
Steve, if you got a second, can we give them a practical example, a really quick one?
I have to do something real quick, so I'm going to turn this over to EO real quick, and you have the floor.
I don't have presentation software though. Drag, can you write? Do you have access to something? So, let's say Sally has dimes and nickels in her pocket. Everyone with me?
I don't have that program, but let me see if I can pull up like Paint or something.
Sure. I mean, so. There are numerous applications. In case anyone is in the chat wondering, why would we ever need this? Oh, it comes up all the time. So suppose Sally has 16 coins in her pocket. Everyone with me? Some dimes, some nickels. Can everyone understand the problem?
Yeah, I'm muted. Yeah, I'm listening.
Okay. Yeah, go ahead.
So I hope you understand
too, so go ahead.
I hope you understand. Not even Stephen Hawking can solve the problem now, because all I've told you is that she has some dimes and some nickels. How on earth would we solve this problem? Does everyone see the problem? We need more information. Yes.
Right.
Yep.
Great. Now I'm going to tell you that the total value of coins in her pocket is $1.60. So now I've given you two equations and two unknowns.
Okay. So in the two variables are the two sets of coins. We know the values of the coins, and we know the total values of the coins, and we know there's two sets of them. So that's all the information.
Exactly.
Yeah.
D for dimes and N for nickels. Now, no matter how much I flatter myself that my voice is smooth, it's going to be really hard to do this without a presentation. So I'll just say the two equations are capital D plus capital N equals 16. Does everyone follow that? She has some dimes and some nickels, and the total number of coins is 16. Is everyone still with me?
Yeah.
I see the gentleman with all the hair nodding. Good. All right.
Yes.
Now we get into a situation where you have to say, okay, each dime is worth 10 cents, so that means 0.10 times D plus 0.05 times capital N equals 1.6. In other words, the total value of all the dimes and all the nickels makes $1.60.
Okay, so we've attached, well, we've turned the amounts of, the values of our variables, which are coins, into decimal form. We've attached the variables to them because those are our unknowns. So we're setting up.
Sorry to interrupt you. Wouldn't using whole numbers be better? I mean, yeah.
I was about to go there. Yes. Hold on. I was about to go there. So the very next step, as Steve did, we're going to multiply the second equation by 10 to make it something far more tractable into something really easy. So it's just going to be 10D, multiply by 100, excuse me. 10D plus 5N equals 160. Multiplying both sides by 100, we get 10D plus 5N equals 160 for the second equation. So now our two equations become D plus N equals 16, and 10D plus 5N equals 160. Sorry, and in the first one, it should be 26, not 16. The first one should be 26 coins, not 16. 26 coins.
Okay. So right now, all we've done is taken the word problem that you've given us. We wrote it out in decimal form because that's the actual values of the coins. We've attached the variable, well, their respective variables, to them, since those are our knowns. And so now we've turned them into whole numbers.
Yeah, it only just occurred to me that if it was 16 coins in total and it totaled up to $1.60, then there's
all
no
dimes.
Nickels. Yeah, it's
Exactly,
just all
yes.
dimes.
Thank you, very good. Okay, so it's 26 coins. Forgive me, everyone. Okay.
Yes.
Now, Drag, I don't know if we should continue because basically what we need to do is multiply the first equation by 5 and then subtract the first equation from the second equation. I just wanted to give an example of I mean, it's a really easy problem. I think it ends up being 10 dimes and 16 nickels.
All right, I got one for you. The trick question, I'll tell you right here now. So you're gonna.
So it would have been $1.80. Sorry, go ahead.
It's an old joke. Well, it's not even a joke, but it's just I have 2 coins that total 2 U.S. American current coins that total 55 cents in my hand. One of them is not a nickel. What are the 2 coins?
Well, it's a $50 and a nickel.
Yeah, the other one's a nickel.
Yeah, the other one's a nickel. There you go. See, I got smart people in here. Everybody get that? One is not a nickel,
Steve,
but the other one is.
Steve, you have access to the software, so we can just type it out. This is it shows a really easy problem to do, but we'll have to visualize
Do I
it
have access to what software?
to whatever you're typing with.
The Desmos.
Oh, I just closed it all out. Oh, I have Desmos. Yeah. What am I typing here for Desmos?
The coins and
Okay, so
coin
let's-
problem.
Okay, I told you I didn't hear any of that.
Okay, so let's just
Okay.
begin again. Sally has some nickels and dimes in her pocket, 26 in total.
Let me screen share. Just give me the formula and I'll type it out as you're doing it.
Okay. Capital D plus capital N equals 26.
All right, one sec. Okay, what is capital D?
Plus capital N
Capital N.
equals 26.
6. Okay.
That's it.
You know what? This program is not. This is not the right program I think to use to do for that. This is just going to graph. This is just going to graph. This is not an algebra program. This is a graphing program here. So you would need like Tiger algebra or something maybe.
What about
That's not going to work.
No, it's
something
just a simple Word
Scilab or
document. will work.
MATLAB?
Oh, okay. I'll go back to math. I'll open it again. 1 sec.
So let me repeat for everybody. Sally has 26 coins in her pocket. Not 16, 26. I'm sorry.
So D plus N equals 26.
Yes. And the total value of coins is, let me be careful here, $1.80. Forgive me. Not $1.60, but $1.80.
Okay, so dn equals 26.
D plus N.
Pull this up.
D plus
Oh,
N.
D plus N?
Yeah.
Okay. There you go. Okay. It
And
stands
then,
for dimes and nickels.
yeah, and so everyone, what I'm about to write is shorthand for we got rid of the decimal. The next step, Steve, is 10D plus 5N.
Let me get a new line. 1 sec. Plus 5N.
Still with me? Is $1, 180. 180.
Thought it was 160.
I changed it.
Fair enough.
You'll see why. But good catch. Thank you, sir. All right. So let me repeat. Steve now has succinctly captured the problem. Sally has some coins in her pocket, nickels and dimes. She has 26 altogether. The total value of those coins is $1.80. And so this is the beauty of math. You can take those 2 English sentences and transform it into something, perfectly succinct and logical. Good. All right, Steve. Now you can run with it, Steve. You can go with it.
All right, so let's say. So if I want to change the first equation, I get to say n equals 26 minus d, right?
Oh, I would really go with elimination.
How do you want to do? What
Steve.
method are you going to use?
No, I would really go with elimination. Multiply the first equation by.
You want to go by
5.
elimination? Okay.
Yeah.
So we're gonna times the first equation. Well, the reason I don't like using the program for this because my other one I have all the alignment and I used actually a matrix alignment to actually make it look normal. This may not work too well. So let me actually try doing it this way. My goodness. Okay, so I don't want to do it that way. All right, this may not come out right. Let me just work with it as is, so I'm not showing different steps because again, it's not going to align properly. It's going to look weird. So I want to manipulate one of these so I can subtract or add them together to get a new equation, right?
Yes, sir.
Okay, so which one do you want to work with? You want to?
So
Do you want to stop by 10?
Right. You can multiply the top equation by 10. That'll
All right,
work
let's do it
too.
that way. So we're going to multiply the top by 10. Okay, so it'll look like that. Okay, so
Right, and I
now
hate to nitpick, but I've never seen that before. We always keep parentheses
grouping.
on one
Yeah,
side.
I know.
I know. But go ahead, sorry. Equals is 260. I mean, yeah.
All right, you want to like that?
Beautiful.
All right. So now I'm going to distribute it over multiplication, right? So I'm left with 10d plus 10n equals 260.
Good.
Right. And I'm going to actually copy this right here and put it down there. And then we have a new line. Okay. So, you know what? It's not too bad. Remember, like I said, I was trying to, on the other thing, I had them all aligned using alignment, but I think this works. Okay. So what do I want to do here, guys? What's the easiest way to get rid of that D?
To get rid of the
Anybody?
D? Let's see. We should probably. What's going on? It's moving around. Okay. Let's see. We can turn this into a negative. Yeah, we can just do the top one minus the bottom one, can't we? Okay. Get rid of the D.
Excellent.
Or the bottom one from the top, right? We're going to bottom,
yeah, either way. Yeah.
So 10D minus 10D is 0, right? And if you want me to show you, it's 0D. I'm going to make a new line here. Line. Hey, Hogtie.
I'm doing dishes as we're doing this.
Okay, so my D's are going to go away, obviously, here. 10N minus 5N is 5N, right? And then 260 minus 180, which is going to be 80.
Excellent.
And and this is just showing you how this would work if you just, do it like this. I'm just going to eliminate the D. Okay, just get rid of it. So it's going to be 5N equals 80. Right, and then what do you think, Midnight, we want to do to get X isolated, or N isolated, as the case may be?
Not sure if Midnight's here. Let's see.
We just want to divide X by 5,
yeah,
right?
Yeah, to isolate that, because that's the only variable left. So we divide everything by 5 to get the N alone.
Okay, and that gives us what?
Was that 5 divided by 80 is, wow, I should know that.
80 divided by 5, buddy. 16.
80 divided, yeah, 16, okay.
Right, that's what I got. Very good. That's what I got. So that's what you got. We're all happy. So we now have we now have one of the two things we need to know, right?
Okay. So now we
know how many
plug them
nickels
in.
we have. Now we can back substitute this in. Let me move this.
Exactly.
This is how I do my command
nickels,
lines.
by the way. Yep.
Okay, so we know one of them. So we're going to pick one of them. We'll just pick the top one, I guess. So we have 10D plus 10. The 16 equals 260. You make a new line. Okay, so does that look good so far? Awesome.
Beautiful.
All right, new line. Let me move this up a little bit so we can get some. There we go. All right, so let's calculate this out. We've got plus 160 equals 260. So far, it's looking really good. And
yeah, then you minus.
Then we take 160 from both sides, right? So we're left with
100. Yeah. So.
Okay. And
D equals.
So D equals 100 minus 10.
No, 100 divided by 10. Careful, Stu.
100 times, yeah, 100 divided by 10. Let me do it this way over 10. Right. New line. Keep having to type thousands of new lines in order to make this appear right. And I left with D equals 10. New line. So now I have both numbers. And are we technically done yet? No. What do we got to do before we can say that this is right?
Yeah, check it. Plug them back in.
Let's check
so
our
I have
work.
10 and 5. Okay, so we got to check the work. With this, we're going to plug it back into. Obviously, I think this one's probably easier. So 10D plus 5N. This just plug and chug it. So 10D. We're just going to type it out. So 100 plus 25. No, that's not right. Let's see here.
100 plus 80.
100 plus 80. No, because N equals 5. Is what we got? Oh, N equals 16. You're right. You're right. Okay, so we got 100 plus 80 equals 180. There we go.
Very good.
And so, boom. This right here validates this right
And
here.
don't forget, though, the first question was Sally has 26 coins in her pocket. So if she has 10 dimes and 16 nickels, that's 26 coins.
There you go. So that's a real world application of solving a linear equation problem.
Did we bore Hogtie to death? I'm sorry.
Well, no, I think he said he was having audio dropouts or something. There we go. He's back.
Okay. Sound test. Hogtie champ.
You coming? Are we coming through now, Hogtie?
Test. Blurred shitty. I was having issues like that last night where
4 seconds.
Yeah, everyone would cut out kind of a little bit, and then it was kind of fine, and then you'd hear something cut out.
So would anyone like to see a programmatic way to solve that same problem?
Go ahead.
I just found a lovely Python program that basically will calculate reduced row echelon form for you.
So does everyone who not program C++ or C use Python?
You're gonna do echelon form?
C++.
Wait, I'm gonna have to use this for tomorrow. Did you find something that'll do lowest echelon form?
I found a Python function, like I can, let me see here.
Well, I mean, I'm going to be doing matrix in the next couple of days, and I'm going to be showing how to people define the low echelon form using Gauss-Jordan substitution method and determining the inverse matrices, using Compton's rule, Cramer's rule, and a bunch of other things. So we're going to eventually get into matrix. That's why I wanted to start with the linear equations, because I think if you don't understand how matrix relate to linear equations, it really makes no sense.
Right, and I've taken linear algebra, so as soon as we started laying out this problem, I'm like, oh, I don't remember all the steps. It's been a while since I've had to do it, but it's like, yeah, this is a standard matrix problem.
Mm-hmm.
And
that's why I want to relate it. Exactly. That's why I did it the way I wanted to show this one, because it really does relate to what we'll be going into, because they are systems of linear equations that we're solving for when we're doing these matrices, right?
Mm-hmm.
So,
I just want to point out, Steve, there are 3 possible outcomes for a 2x2 system of equations, which you highlighted today. There are only 3 possible solutions. Either the lines are parallel, and there are no solutions. The lines aren't parallel, but not the same line, and you get one solution, like you did with the example you chose.
Mm-hmm.
Or they're the same lines, and we get a degenerate where it's the same line and you have infinitely many solutions.
Yeah. So
infinitely dependent, infinitely independent, and
let's make sure we get this point. That's a very, very good, astute thing. For a linear equation, there are 3 possibilities: no solution, one solution, or infinite solutions. You can never have 2 sets of solutions for a linear equation. It's only
I'd like
infinite.
to point out that no solution is parallel.
What's that?
I'd like to point out that the no solution one is parallel. The one solution one. What?
Graphical explanation so folks see what we're talking about.
Yeah, do that, Steve.
Hang on. Let me go back to my program here.
So I'm still doing dishes, but while he finds that, so people in the live chat, I know some of the folks watching are Mathiverse, and I used to be one of those people too. No, there's people who are interested, because we're at the 12 viewers now, so people have been staying with us. But some of them who are watching, I know, aren't really too keen on what this means. Like, what? Okay, so it's parallel. So what? Like, what is that? Why is that significant? So
okay, well, the parallel would be what I had here before, from the original one to this one. These are parallel with each other, right?
No solution.
There's no solution, because these are not intersect anywhere. There's no place where they will intersect. So there's no solution here.
There's no variable between those 2 equations that will solve both of them at the same time.
And I'm not sure how I'm going to show the other 2 things for an infinite, unless it's because an infinite is just basically it's a self. It's just like you said, a degenerate thing.
You can use different colored lines to superimpose on each other. Is what?
Yeah, you know what? How about that? I actually have done that. I've done that here. These are.
Just do like y equals 2x plus 3.
Well, can you see the different line color?
Yeah, little by little. Yeah.
It's one's darker than the other, but yeah. So that's infinite solutions.
Yeah. Because each solution is going to be on the same exact thing, right?
Right.
And then, of course, one solution in this case would just be my original function, where I have x is, if it's 0, well, 0 plus 0 equals y. On a function, if you guys remember, the y being the dependent variable is dependent upon x, and it always has a one-to-one function to be a function. You put one thing in, so you should get one thing out. Okay, so if I have 0 in x, I can only have one value for y that works, right? Because if I put 0 in here, 0 plus 0 is 0. I can't have 0 here and have 5 there, or 10 for x or y. So it is dependent upon the x variable. So that's something really important to note, that these solutions will only have one of three things: single solution, infinite solution, or no solution. And that does come into play a lot. Now, I want to show you something else. I forget what it was.
See, when you get a second,
Anyways, go ahead.
I want to make a historical comment. What we're doing today goes back to ancient times. There's this ancient Indian problem with, chickens and goats in the yards, and it's exactly like this because chickens have 2 feet and goats have 4 feet. I want to point out the Babylonians solved quadratic equations all the way back to, I want to say, 2500 BC, 2700 BC. Why am I bringing this up? Without speaking to the truth, without speaking to the resolution of the great debate community, I want to point out that what Steve's taught you today, everyone in the world does the same way, basically. They might use different notation, but it's the same way. The Babylonians, when they solved their quadratic equations, basically did it the way we do it. They might use different number system, but it's exactly equivalent. I just want to point out that, there's unanimous, widespread, 100% agreement how we do this, whereas in religions and philosophies, you cannot find two people who agree on anything. Sorry, I'll get off my soapbox now.
Math is the universal language. And I want to clarify, when he's talking about quadratics, he's talking something that's similar to this, is when you have an exponential function, which is going to give you a parabola, and then you actually will have, it actually is in this form. It's ax squared plus bx plus c, which is actually in this form. Is your general form equals 0.
As I mentioned in my broadcast earlier, that like people have done quadratic equations, but one of the things that I learned just recently is that it's used to solve chemical equilibrium problems. It's very, very useful for chemical equilibrium problems.
And Dragnaut hopefully will be doing a presentation on this channel on quadratics. And what I would recommend is start with something simple like this, like a parabola, and then show how to shift it. Right, because if you go, remember the form is ax squared plus bx equals c, right? And the bx will tell you where it's going to be on the y-axis, right? So if I have +5, my y-intercept is here. If I have -5, where do you think it's going to be? Midnight or somebody?
Way the fuck down.
Way down here. Now, if you guys remember, see if you guys remember this. If I put a negative sign in front of the x squared, what do you think is going to happen? Now, hopefully I'm right on this. What do you think is going to happen?
Hold on. It shifts to the right.
Midnight should know.
It shifts to the right.
No. What happens to the
Actually, nothing.
No, it actually does something.
Does it compress?
No. It inverts.
It inverts. Oh, yeah.
Oh, right. I missed it.
Right, because now it's approaching. It's approaching from this quadrant. Oh, by the way, we should go over quadrants. If I remember correctly, this is 1, 2, 3, and 4. Is that right?
Top right is 1.
1,
top
2,
right is 1.
3,
No,
4.
top
Right is 1.
Yeah, going counterclockwise, starting from the top right quadrant.
Not to split hairs, but I know most of math is essentially designated, but with the quadrants, I think we don't have to worry too much. As long as everyone knows what you mean when you say this quadrant, that quadrant, you're good.
Yeah, but I mean, there is official way. I know that this is quadrant 1. This should be 2. This should be 3. This should be 4.
No.
Is this 1?
In textbooks, they'll refer to quadrants just by quadrant. There'll be no picture, so it's important everyone has the same picture in mind.
Okay, so what?
You're the top right quadrant is 1.
Yeah. Okay. You said no, and I'm like, okay, I'm scared now.
No. I'm saying it's important that we all agree.
Yeah, I think it's important to know what quadrant is.
Well,
as long as we all agree.
Yeah, it does come in handy when you're doing what is it with the triangles, and you have to find the there's a particular equation you have to use to find a side, and that side depends on what quadrant it's in. I can't remember what
law of sines. Oh yeah. Law of sines and law of cosines. Exactly. Yeah. To solve. Yeah, for sure. You need to know.
And I should actually point out, actually, you know what? It's not the x. It's not the 2x. It's actually the c that actually determines the y-intercept. The value here. So without
y-intercept, but the x is where the x-intercept happened.
Yeah, the second term.
That's a polynomial equation.
There's a really easy way, fellas, to remember intercepts. To find the y-intercept, set x equal to 0. To find the x-intercept, set y equal to 0. That's the easy way.
Well, actually, no. Right. Well, to find if you're trying to find a vertex, why don't you do b divided by negative b divided by 2a to find the x, and
that's the x. But we were talking about intercepts.
Yeah, we're talking about intercepts.
Oh, right. Yeah.
The thing is this. Look at it. If I set y to 0, right, then my x-intercept should be 0 squared, which is 0. So I'm at 0 here, and vice versa. If I set x to 0, my y should be 0. So my origin here, 0, 0, is my vertice for the parabolic curve. So there's an easier way to remember that. Just whatever you want to find for your intercept, set the other one to 0. So
right, and for American
and
fans, if you think about football, intercept means catch, right? You know, pick off. So for Americans, intercept is easy to remember.
Yeah. All right. So anyways, that kind of concludes this particular presentation. Else, I don't want to bore people too much, and I want to keep it kind of relatively short. I will be working on a Matrix 1 eventually. If there's other things that you want to know about,
let us know. Some, if there are folks out there who've always struggled with, and I hate this, a dirty term, word problems. Word problems.
Oh yeah.
I'm not a big fan of word problems. I'll do them.
People hate word problems. I have learned to appreciate them, and that they are like the ones that are a challenge are really fun to do, except when they start getting into a little bit of trig, and then that's when it's like, oh fuck me.
Yeah. Speaking of trig, I would like somebody to do some trig presentations. I will be happy to do basic trig, not a problem. But eventually, when we start getting into things like hyperbolic functions and arctangents and all that kind of really shit that we hate, and especially differentiations of trig functions, I'm going to be out of my league on that one. I don't remember that at all, and I don't want to relearn it right now in order to be able to explain it. I'll relearn it if somebody does a presentation, but that's getting to higher level math that it will require a little more expertise than I have, and I'm fully prepared to state that. Right? Even Scott's going, yeah, that shit sucks. Yeah, it's no joke when you start using derivatives and integrals of like cosecants and all that stuff. It's God. It's a nightmare. It's a freaking nightmare.
I mean, if you want to get bent over. Yeah.
I mean, I did up through Calc 3, and I mean, even then, you only lightly brushed that level of complexity.
Yeah, it's ridiculous. And so I'm woefully out of my league on that. Do I understand the principles? Well, sure, a little bit. We all kind of do. They've had calc, but yeah, it's just not fun. I don't want to do it, so whatever. So if somebody wants to do trig, I will be happily allowing them to do trig. Except for, like I said, I might do a basic one on just basic functions, right?
Right. I mean, as long as you're just working with like standard geometry, trig isn't all that confusing. It's when you start applying trigonometry to like really complex problems, but like 2D geometry, it's pretty easy.
Right. I agree with you. And that's why I'm just doing basic stuff. Everything I've done so far is just review pretty basic stuff, except for the Calc 2 one I had on Taylor. That's really not that basic. That's actually kind of advanced, but I don't think it's that difficult. That's why I was able to explain it. I think halfway.
We were just going over a proof. We are just doing the same thing. It was finding derivative of the derivative.
Yeah. Well, hey, you know what? Eel's the math guy, and he said I did a pretty decent job. So I was kind of stoked about that. That made me feel good.
Today also, and I was just going to say, I see the future. You and Redline can do a crossover episode with some of the trig and flat earth stuff.
Are you surprised that I remember math as well? Because I don't talk about math that much. I've always said that, I've got a background in what I have, but I don't use math a lot. But I'm actually surprised myself that I do remember this stuff as well that I do, that after I can explain it, right? Because anybody can remember it, be able to explain it, it's a different story.
No, you've done fine, and you have an engineer's mentality. Like, it's funny because I can certainly tell your training, and so that's great. And Dreg, you would have done well in math. I mean, don't sell yourself short. So let's get.
Yeah, I know. You could tell. Yeah, that was a slight, by the way. That was an insult by him. It was kind of a backhand compliment, because engineering backgrounds hate math, and we're very sloppy.
Yep. They're very utilitarian. They're very utilitarian is a better way of putting it.
So he could tell the difference.
Math is a tool, not a lifestyle.
I went to school for originally EE, switched to computer engineering, but yeah, no. We want a utilitarian grasp of math.
Hey, speaking of computer engineering.
Wait, Scott, guess what? You're nominated. You get to do a presentation on Fourier transformations.
Oh God.
Oh, can I just if there's even one viewer, hang on, guys. If there's even one viewer that caught Steve's Taylor series presentation, what's really cool is, this brilliant French mathematician Fourier proved that any periodic phenomena, in other words, anything that kind of repeats itself continuously, can be modeled using sinusoidal waves. And this is exactly what they do with Fourier transforms. And this is precisely what made, compact discs and other stuff work. So it's a fundamental discovery.
I'll tell you what, I will do, if I get time, I will do a Taylor series presentation on like sine of X or cosine of X or something, right? Because I think it's kind of important. It's a little more challenging than the one I did, but it's doable. I know the Taylor series for it. That will lead in to the Fourier transformation and why we use that to go from the frequency domain to a time domain and what it's for. So if somebody wants to do that, maybe Scott has been out of a long time, but if you do know about electrical stuff and you know about wave functions, that would be a good presentation, because I find those things to be fascinating. Waves are cool. Waves are cool, but the formulas for waves are confusing. They're complicated, but again, this is the Great Debate Community math portion, and I want people to be able to do these presentations, and hopefully people find them interesting.
I could even see, Steve, if you ever got a touch screen where we could just have someone come in, and if they wanted to ask something basic up to even like, undergraduate math, we could just, I guess it might turn into a homework solving session. So I'm not sure
Well,
if that's where you want to go.
I was going to put a touch screen on my wish list, but I don't know much about them. I don't know what would work with what. I have no idea what I'm looking for. So anybody out there, any recommendation of what a good touch pen program would be, where we could do this in writing it out, I would be happy to do that if somebody wants to fulfill my wish list. And that's for people that are affluent enough to do that, not poor people like most of us here. But there are some affluent people in the community that have asked me to put things on my wish list, and I've actually said no. I've already had my wish list done 6 months ago, and I said, if I ever come across something that I need, I will let you know that can help with this. And so I think that would be a good thing for the wish list.
You pass up a good opportunity. I asked for a bag of dicks, but that's just me.
No, I got the bag of dicks.
Oh, hey, Steve. Actually, have I actually thought of an idea. Why don't you put a link to some practice problems in the link? Of each math video you've done. Should have mentioned this before you started. So so that way people, they can look at how you did it, but they can also try some on their own.
You know what? It's a little more time consuming than I want to do, to be honest with you.
Fair enough, I guess. I don't know.
Steve, in my defense, electromagnetic field theory was the class that made me go, I'm switching to computer engineering.
Oh yeah, no, dude, I'm with you. When we were learning about wave function and waves and all that shit, I was just like, oh my god, please let this end.
I was ready to check out at 3D vectors.
Well, we had
thank you.
Well, we had vector analysis. So that wasn't excruciating, but
I was already full up on vectors at that point.
So you did a lot. Did you do topology and 3D vectors, topologies and manifolds?
We were doing mostly like field analysis, but for me, most of my vectors was just standard statics dynamics, and that was plenty of vectors for me.
That's fun. That's a lot of fun.
So
statics was not too bad. Dynamics was rough.
This stuff most people will never be exposed to, so I don't know how deep we can go in a lot of that stuff. I think matrix is important. I think matrix, eventually people all get into some form of matrix. Even if you just take college algebra, you get exposed to matrix.
Yeah.
Really, the concept of matrices.
Yeah. Mm-hmm. So what other subjects? I mean, real quick. I mean, I want to end this, but I'm kind of enjoying this conversation. If we have
we can do some fun stuff in number theory, Steve. I mean, like
number theory.
You know what?
So like set build. You want to like learn set builder notation, maybe?
Well, or that, or just even you could just bring up, Fermat's last theorem. The solution's difficult, but the presentation's easy, right? You could start with the Pythagorean theorem and go to Diophantine equations. I mean, there's so many things.
Oh yeah, that's easy, yeah. And Fermat's that theorem was for a squared plus for a to the n plus b to the n to c to the n, and there's no value for an integer of n that satisfies over n equals 2. Is that what it is?
For any integer, so for 3 or greater.
Anything over 2. Yeah. I remember that.
I'm trying.
People think You know what's funny? I'm always accused. Oh, Steve's just Googling this stuff all the freaking time. It's like, no, I actually do remember some of this stuff.
Yeah. I'm over here doing dishes. Like I'm just going based off fucking memory while I'm looking at. Like the only reason I didn't actually pass calc is because I had 2 part-time jobs for a full-time student, and I had to pick up my son right after I get out of class. So that doesn't leave that much time in between my other classes and other responsibilities. Not that I couldn't do it, but I needed more time to dedicate to it. And so you learn your limitations.
Huh. Yeah, yeah, exactly.
Steve, besides at one point, did you mention Carnot mapping?
What's that, Dave?
Carnot mapping? At one point you mentioned Carnot maps?
I don't know what that is.
Oh god, it's they use a lot in digital electronics.
I know about mapping as far as mapping functions, or like f colon like r to r, where you have an r and you draw a line as r, or you map like the complex planes. These are using what's called bijection, surjection, and injection. I hate that stuff. I could do it, but I don't really want to have a presentation on it because it sucks. But if somebody else wants to, you know what? That's a good presentation though. If somebody wants to explain the difference between bijections, surjection, and injection, go for it.
Well, we can do that right now. That's really easy. One-to-one onto, etc. But
separate presentations.
I'm going to save it for another day.
Here's the mathematician in the room going, "Oh yeah, this is just
no." Here, really
Child's
simple.
play.
Everybody, here's a simple injection. You can only have one weight, so we'll map everyone onto his or her weight. That's an injection. Everyone with me? But it's not But there are so many different kinds of weights that it's not a surjection. Like Steve said, we can do it later. But
that made it more. I know what they are, and I didn't understand what the way you put.
Well, an injection is a one-to-one mapping.
It's a one-to-one map.
One-to-one mapping.
Right. It's from the F group F to assuming to Y to X. It's a one-to-one correspondence. But aren't all bijections both surjections and injections?
Yes, that's the definition of bijection.
Right. So, yeah, I kind of remember this stuff, but like I said, I don't want to do a presentation. This stuff just kills me.
All right. Well, on that note, folks,
right.
let us know. Let us know what you want. If you suck at word problems, I will go and dig up my physics word problems and we can go over like the simple ones. Simple.
Yeah, by the way, eventually I do want to get into some physics stuff.
Not like optics.
The one thing that I kind of do know how to explain is Carnot efficiency, and explaining how you have a 4-step process where you have an isothermal reaction, and show how the work is related to the integral under the curve. And there's different formulas for that. And that I do remember. I like to do a presentation on that if anybody's interested. And then maybe some other physics stuff that I remember. Somebody had asked me to do a presentation on Lorentz contraction and how it relates to time dilation and special relativity. That would be easy. That's a no-brainer.
Yeah, I actually wish KC would do a presentation. I mean, I know he's busy with everything else, but
come on.
What about a presentation on like Boolean algebra subjects? Because I feel like that's a section that I might be able to contribute.
That would be awesome.
That would be awesome.
That's what I was getting
Because
at,
that's
too.
really kind of in my wheelhouse these days. I write code, like that's stuff I have to think about all the time.
How about we
do that,
set something tomorrow?
Awesome.
Could you and David get together today and have something tomorrow and we can go over Boolean values?
Well, not tomorrow. Tomorrow. Wait, what is it? Monday?
Oh no, tomorrow's Wednesday. No. You have the thing with Dr. Fuzz tomorrow. Tomorrow's Wednesday, right?
We got 2 things tomorrow. Yeah, we got Dr. Rana in the morning and we have Dr. Rhodes in the afternoon. So
how about we do
kind
a
of full day.
Friday special, all Boolean, all Boolean all day.
All
Fuck
Boolean.
You guys will know where my name came from, for fuck's sake.
I know where it came from. I've taken a JavaScript class when I was in high school.
Oh, JavaScript.
JavaScript has come a long way since.
Well, Scott, are you going to be presenting it from a computer point of view, like for scripting, or are you going to be presenting it from just a Boolean algebra point of view?
I mean, I would say start with. I would say I would want to look up material and brush up to make sure I've got all the terminology. But yeah, I would start with the basic Boolean algebra, truth tables, your general Boolean
logical operators,
conjuncts, independent events. Yeah,
exactly. And
no, that'd be good.
Because I feel like that not only appeals to people who are maybe looking for that technical aspect, but it also applies a lot to philosophy.
You know what? I was going to say the exact same thing,
right?
Because obviously with propositions,
predicate logic.
Propositional logic, especially if you can relate to Boolean, what you're going to be doing the operators to Boolean logic and propositional logic, that's even better because these are intertwined a lot. Obviously,
Steve, what's his name? Scott.
Yes.
Scott here.
Are you? Is your logic good enough? Do you understand axiomatic systems? Because I hear lots of people refer to them, and I'm happy to be second or third mic on a podcast, but it seems I haven't found anyone yet who, I guess probably Dr. Malpass knows about logical systems. But I mean, do you know about like independent and consistent and complete and how?
I think that's diving a little too deep into the subject even for me. I mean, as I said beginning, I have an engineering background, so like Boolean algebra for me started from a practical standpoint, learning the Boolean functions, how they behave.
Yeah, I've looked at
and or exclusive or not.
I have no idea what the hell's going on.
Exclusive and or NAND.
I have a better chance of learning Russian than I would ever learn those types of logical systems. It's that confusing.
But yeah, I added you on Google Plus. Just thought I'd say that, Scott.
All right, cool.
But that's what I was talking about with Karnoff mappings, Steve. Is that's a way to reduce a logical circuit, if you will, to its most basic form for the number of gates you use to make a decision.
So you would use that if you, so example, if I was working with like a TTL system, and I have a bunch of gates, that would be able
Right.
to, okay. I get the principle because I've worked with TTL and I've also worked with CMOS years ago.
Right. And the Karnoff map is ironically it's basically a binary matrix because you take a truth table and you can reduce it out. So it's kind of fun.
Yeah, that'll define a lot with what I'm going to be talking about with matrices then. Sure.
I actually, it's like literally in my brain, I'm like, yes, I know Karnoff's maps and I know related to truth tables, and I was going to say, yeah, the same kind of theory that you do for like a lot of matrix theory is this a lot of the same ideas that you're working with truth tables and things like that to reduce down the system to just give me a combination of inputs, tell me the output.
See, this is going to be fun. I'm glad that people are getting interested in the Great Debate community channel to do math stuff. I know people are running the philosophy hangouts, but I'm glad people are going to be doing math hangouts. And then maybe we can have somebody do like astronomy or astrophysics or chemistry. Eventually, the goal is people come in and they have something they talk about and explain it. I think that's going to be great. Don't you guys think that? You know?
That's a heck of a goal for a channel, and I like it.
I think it's definitely doable. And once we get big and popular, we'll have Ronnie come in, and Ronnie can explain biochemistry to us. That's my goal. That would be the shortest hangout in history.
Please stop.
It'll be. Let me explain to you all I know about biochemistry. Thank you for watching.
Well, actually, no. I want Edgar to prove that he's a what is he, a civil engineer or something? All the shit that he says.
That was Edgar. But it reminds me of a joke that I had a long time ago, and I'll end this hanging on that. I used to write jokes, but one of the jokes I wrote was, I've always wanted to be a sex education instructor so I can go in and say, okay, everybody, I'm going to be teaching you all I know about sex. Class dismissed. And there you go.